Machine learning. You hear that phrase thrown around all the time, right? It's in our phones, it's in our healthcare, it's pretty much everywhere. But what does it actually mean? Well, in this explainer, we're going to pull back the curtain and demystify the whole thing. We're going to break down, step by step, how a machine actually learns.
I mean, have you ever stopped to think about it? How does your phone unlock just by looking at your face? Or, how does your email inbox just know which messages are spam and which aren't? It feels like magic, but it's not. These are perfect everyday examples of machine learning doing its thing. So, okay, let's get to the core definition. Fundamentally, machine learning is about teaching computers using data. Think about it this way. Instead of a programmer trying to write millions of if-then rules for every single possible scenario, we just feed the computer a ton of examples. The algorithm then sifts through all that data and figures out the patterns for itself to make predictions. It learns on its own? Okay, so first up, what is machine learning, really? Now, this whole learning process, it's not just some kind of digital magic, right? It only works when certain conditions are met. Let's dig into what those are. So it really boils down to three key ingredients. First off, a pattern has to actually exist in the first place. I mean, if the data is just random noise, there's literally nothing for the machine to learn. Second, that pattern can't be super obvious. If you could just write a simple math equation to describe it, you wouldn't need ML. And third, and this is the big one, you need data. Lots and lots of data that actually contains and showcases that pattern. All right, so now we know when a machine can learn, but the real question is, how does it actually do it? To really get our heads around this, let's walk through a pretty high-stakes example, using machine learning in medical diagnostics. So let's put ourselves in the shoes of a data scientist. Our job is to build a tool, a model, that can help doctors predict if a patient has a certain disease, all based on their test results. The goal seems pretty simple, right? Is the patient sick or are they healthy? It's a classic machine learning problem, but when you're talking about medicine, figuring out what success actually looks like is, well, it's absolutely critical. Now, any prediction our model spits out can end in one of four ways. It can be right in two different ways, and it can be wrong in two different ways. And understanding these four outcomes is the key to figuring out if our model is any good. And this grid right here is what helps us do that. It's called a confusion matrix. And yeah, it sounds a little intimidating, but it's actually pretty simple. Let's break it down. A true positive, that's a win. We correctly said a sick patient is sick. A true negative is also a win. We correctly said a healthy person is healthy. Easy enough. But then you have the mistakes. A false positive is when we tell a healthy person they're sick. And a false negative is when we tell a sick person they're healthy. And this is where it gets really, really important. Not all mistakes are created equal. Think about it. A false positive, that causes a lot of unnecessary worry, maybe some extra tests. It's not great. But a false negative? Whoa, that means a sick person thinks they're healthy and might not get the treatment they need. So you have to ask, which of these errors is worse? We have to decide which one we're more willing to risk and then tune our model to avoid the more dangerous one. So that leads to our next big question. How do we actually measure how good the prediction is? How do we quantify this trade-off between different kinds of errors? Is there a way we can just, look at a chart and see how well our model is doing? Well, yes, there is. This chart is called an ROC curve, and it's basically a report card for our model. That straight diagonal line you see cutting through the middle, that's just random guessing. It's no better than flipping a coin. The goal is to get our model's performance, that colored curve, to bow as far away from that line as possible, up and to the left. A perfect model would shoot straight up the left side and then zip across the top. The bigger that arc, the better our model is at telling the difference between who's sick and who's not. Now, as we're trying to build this amazing, super accurate model, there is one giant trap we have to be super careful to avoid. And that trap is called overfitting. The best way to think about overfitting is to imagine a student studying for a big exam. One student actually learns the concepts. The other just memorizes the answers to the practice test. The memorizer might ace the practice test, but they're going to bomb the real exam. An overfit model is like that second student. It has memorized the training data, including all the weird little quirks and random noise. So it looks like a genius on the data it's already seen, but the moment you show it something new from the real world, it completely falls apart because it never actually learned the real patterns. To put it a bit more formally, the model has latched onto patterns that are only in the training data and just don't apply anywhere else. It's basically seeing ghosts in the machine. It's finding patterns that aren't really there in the real world. And avoiding this is honestly one of the single biggest challenges in machine learning. So how do we fight this? How do we keep our model from just memorizing? Well, the standard solution is to split our data into 3 separate buckets. First, you've got the training set. This is the data we use to actually teach the model. Then there's the validation set. We use this to tune the model's settings and, crucially, to check if it's starting to overfit. And finally, you have the test set. This is a chunk of data the model has never, ever seen before. This is the final exam, and its score on this set gives us our best, most unbiased guess at how it'll perform out in the wild.
Okay, so we've covered some really core concepts. Now let's kind of zoom out a bit, because machine learning isn't just one single thing. It's a huge field with a bunch of different flavors, you could say, and they're mostly defined by how the machine is taught.
Really, the 2 main branches you'll hear about are supervised and unsupervised learning. With supervised learning, the data has all the answers already included. It's labeled. It's like giving the algorithm a study guide that already has the answer key. But with unsupervised learning, there are no labels. There's no answer key. We're just giving the machine a big pile of unorganized data and telling it, hey, figure it out. Find the hidden structure in here all by yourself. That medical diagnosis problem we talked about earlier, that's a perfect example of a type of supervised learning called classification. We're trying to put things into categories or buckets. In that case, sick or healthy. Another big one is regression, where instead of predicting a category, you're trying to predict a specific number. Like, what's the price of this house going to be, or what is a person's life expectancy?
And for unsupervised learning, a classic example is something called clustering. Imagine an insurance company that has data from thousands of different zip codes. They could feed all that data to an unsupervised algorithm and have it automatically group together areas that have similar kinds of insurance claims. The key thing here is they never told the machine what to look for. The algorithm just found these hidden groups all by itself.
Pretty cool, right? So after seeing all of this, how machines can find patterns, make predictions, and even uncover hidden structures in data, we have to ask the big question. Is the machine actually intelligent? Well, here's the thing. At the end of the day, machine learning is an incredibly powerful tool for recognizing patterns, and it can do it on a scale that we humans just can't. But what it doesn't have is common sense, or context, or consciousness. The real intelligence isn't really in the algorithm itself. It's in us. It's in the way we, as humans, decide to use it, the questions we ask, the data we give it, and the problems we choose to solve with this amazing technology.